So Ahan belongs to the Mobile Network Systems Department at Nokia Bell Labs in Murray Hill in New Jersey, where also one of the OAI workshops has already taken part, I believe, in the past. He obtained his PhD from the Georgia Institute of Technology in 2021, and since then he works at Nokia Bell Labs, and he's working on 6G networks, or open radio access networks, non-terrestrial networks, and software-defined networking. And he will now speak on A1 policy-driven RAN slicing with the OSC rig and OpenAirInterface. So please welcome, Ahan.
Yeah, please go ahead. I just left my.
Oh, okay.
Yeah, thanks for the introduction, Robert. So today I'll be talking about some of the work we've been doing that kind of integrates different software components from OAI and OSC towards sort of realizing or building a end-to-end ORAN reference implementation. And the use case that we have been targeting as part of this work is essentially achieving A1 policy-driven RAN slicing that leverages the OSC rigs and OpenAirInterface. So I'll be talking a bit about that. So to start off, we have the standard ORAN architecture that we see here. You've got your different rigs, you've got your RAN, and so on, right? And as part of this use case, what we've really focused on is using or extending the SMO from the OSC. And then we have some extensions for the OSC near real-time rig is what we call hex rig. And then finally, of course, the RAN that we're using is primarily based on the OAI RAN stack, right? And I'll talk a bit about each of these components. And then towards the end, we also have a short video that kind of showcases in a demo environment what an integration of this kind would look like. So starting off with the first component, this is the SMO that, of course, is coming from the OSC, borrows a lot of components from the ONAP project. And within this context, what we really want to focus on is the non-real-time rig aspect, really, right? That provides your A1 policy ultimately. And speaking about the non-real-time rig, as part of this use case, what we've done is that we've added a RAP, right? And we call this RAP the QoE-driven slicing RAP. So the idea is that, say you're talking about emerging applications, and in the demo we'll showcase, say, cloud gaming and mixed reality, right? So for these applications, say you want to specify what could the QoE be, right? So say for cloud gaming, you talk about the QoE being FPS, right? So you provide these kind of inputs to your RAP, and then the RAP should, in a sense, create a policy, an A1 policy that's sent over the A1 interface, right, towards the near real-time rig that sets the corresponding slice requirement. So not super clear here, but on the right, we have an example of a resulting A1 policy, and this essentially sets the throughput requirements for the corresponding slice. So say you have mixed reality slice and you input a QoE corresponding to, say, detection accuracy, right? So what would the corresponding throughput requirements be? That's what the RAP tries to do, right? And then this policy is pushed towards the near real-time rig. Once we get to the near real-time rig, so I'll talk a bit about that. So at the near real-time rig, we're receiving the policy over the A1 interface. And we call this like the hex rig. It's largely based on the OSC-G release with certain extensions to support RAN slicing, a slightly more robust messaging framework, and some support for machine learning lifecycle management, right? So for this demo, our key focus here is on these three XApps really. So you have the LAN telemetry XApp, the RAN slice configuration XApp, and the slice assurance XApp. And together, these three XApps are what enable your closed loop automation for RAN slicing, right? So the idea is that, okay, over the A1 interface, you've received a specific policy for your slice, and then this is where your CLA kicks in. So your slice assurance XApp will use the telemetry XApp to trigger a subscription, and then the information that you receive on these indication messages will then be acted upon by the assurance XApp to see, okay, if the SLA is not being met, do we need to make any changes to the RAN slice configuration, and that's then pushed over a rig control message over the E2 interface. Some other aspects that are not being featured as part of the showcase here are, but I'd still like to talk about them, are this notion of a meta messaging framework. So those of you all who are familiar with the OSC rig would know that it uses the RMR or the rig message router, right? So we have tried to sort of abstract some of the complexities of the RMR while also allowing for additional messaging transport. So you want to use native 0MQ, or you want to use Kafka and so on. So you could do that, of course, in addition to RMR. And then the other aspect that we've worked on is sort of bring the notion of ML ops or machine learning operations to the near real-time rig, right? And here we've tried to sort of provide a full suite of lifecycle management tools that are integrated within the near real-time rig. So all your retraining, deployment, so on for machine learning models is sort of done in an automated manner, right? So the key goal here is that the RAN and the rig should be sort of abstracted away as a black box. If you're working on different use cases, you sort of seek input from the RAN and the rig and then provide your parameters to the rig, not necessarily concerned about the complexity that's in the underlying network. And then here, what the near real-time rig is doing is that we've talked about how the indication and control messages are being sent over the E2 interface towards the RAN, right? So we go on to the RAN. And so this is what we call the hex RAN platform. I mean, it's largely based on the 3GPP protocol stack from OAI, in addition to certain extensions to allow for easier programmability and interfacing with the different rigs. So the idea here is that, okay, you've got your base protocol stack right at the bottom, but then on top of that, we build a mediation layer that sort of abstracts or rather provides protocol level abstractions to any other consumer at a higher layer. So for example, within the context of ORAN, this could be an ORAN RAN function, right? So you have this ORAN RAN function that's interacting with the mediation layer. And then the mediation layer is the one that's enforcing changes within the protocol stack. And as part of this mediation layer, like one example implementation is a RAN slicing framework that we'll be using for the demo, where essentially the slicing framework tries to enforce slicing in line with the 3GPP NRM or network resource model, right? So we've got some extensions for that. And finally, on top of all this, you have the HexRAN agent, which is your gateway to all external components. So this would be your SMO, this would be your near real-time rig, and so on. So this is implementing your E2 and O1 interface. At the same time, it has capabilities to allow for RAN sharing, where you have different near real-time rigs interacting with the same base station in a sense, right? So bringing all of these together, this is in a sense the end-to-end reference implementation that we've set up that leverages different components from the OSC software stack and the OAI software stack, right? And as part of the showcase, you've got essentially two DUs here that are connected to USRPs over UHD, and then you've got each of these DUs is connected to its own CUUP. They're sharing a common CUCP, and then you've got a local UPF that's connected to the application servers you'll be showcasing. Then you have another external UPF that's sort of connecting to the internet. So the UPF and the other core components are from the Open5GS project, and then you've got the OSC near real-time rig and the OSC non-real-time rig. And we have tested this setup against a wide variety of COTS, UEs, and modems. So UEs from Sony, Motorola, Samsung, so on. And of course, it goes without saying that since this is based on OAI, all of these UEs are also compatible with OAI and should have no issues connecting with an OAI based base station, right? And upon this testbed, right, since we are talking about A1 policy-driven slicing and specific applications, so we've deployed a number of different applications in different slices. So slice one is the mixed reality application, and what we have here is essentially a pose detection and holographic projection application. So how it works is that on the other cell, the cell 2, you've got a Z camera that's tracking the user's movements, and this video is then being streamed over the cellular network in the uplink and then back on the downlink to the user in slice 1, where we've got pose detection algorithms running on the system here, which are then projected on to the headset. So that's about slice 1. Slice 2 is your cloud gaming slice with a fixed wireless use case. So you have your cloud gaming server in the cloud, and then your fixed wireless users, a modem connecting there, and they are sort of playing this game, and all these interactions are happening in real time, but then the game is being streamed from the gaming server. And then as background traffic, we also have VoIP, but we won't be focusing too much on that when the use case is just there to sort of complete the gamut of applications that exist. And the other aspect I want to touch upon is that the users in slice 1 and slice 3 are experiencing mobility by way of a mobility testers, this like small device that's varying the over the channel, whereas the user in slice 2 will not be experiencing mobility, and this will be one of the key aspects as part of the demo. Then on the network side, you've got the SMO with the RAP, you've got the RIG with the XApps, and then of course we have our OAI-based RAN connected to the different core components. And a quick overview of what we can expect to see as part of the A1 policy showcase is that you start off with a QoE policy, right? So since we're focusing on two specific applications for mixed reality, the QoE we are looking at is the key point confidence. That's how confident your detection algorithm is of the landmarks of the human pose being detected. And the QoE for the cloud gaming use case is frames per second. So what FPS can you achieve at the user, right? And this information is conveyed over an API provided by the RAP. Now, at the non-real-time rig, this QoE information is being converted to QoS and being packaged in an A1 policy that complies with the A1 TD spec. So as we can see here, essentially you specify the slice ID and what kind of throughput and how many users you would like the slice to have, right? And then you push this policy to the near real-time. The near real-time rig is going to trigger the slice closed loop automation if it's not already activated, and this sort of sets off your chain where you send subscriptions, monitor statistics, and in case you detect any SLA violation, you sort of try to meet your SLA requirements through the rig control messages. And all of this finally comes down to the RAN, where you sort of say a source of statistics, and we enforce slice configuration, right? And each time we change the policy, we can expect this loop to sort of repeat, and that's what we'll I guess showcase through the video. And I guess without further ado, I'll get started with the video. So here, yeah. Right. So the first step is, of course, bring up the network. So we'll bring up all our network functions and attach the UE. So we just have the non-real-time rig and near real-time rig here on the right-hand side, showcasing the different pods that are running, and we'll just log into the relevant one. Then this is the OSC non-real-time rig GUI. Initially, we see there are no policies because we have just set up the network, so there are no users or any specific applications we are targeting. With that, we first start off the core network. So this is 5GS based core network, and once that is up, we'll move on to the RAN. Right, so on the left-hand side, we have the CUCP and then the CUUP on the right-hand side. We'll get those started up too. So once the CUCP comes up, it sends a E2 setup request to the near real-time rig, and the content of which is shown on that screen. Similarly for on the CUUP. And we see that, okay, the request is successful, and then we send a response. Similarly for the DU. So this is the DU corresponding to one of the cells. We won't be showing both cells. Right, and with this, we can bring up our users. So we bring up the VoIP user in slice 3. And we see that, okay, this user is attached. It's assigned a specific slice based on the configuration in the code for that bearer. So slice 1 is the MRU, and that's a modem. So we'll bring that up too. And then similarly for slice 2, which is the cloud gaming. So there's also a fixed wireless modem, so we bring that up too. Right, so once that is done, sort of the network is running. We've got our UE register and the PDU session set up. Now we can launch the different applications. So we begin the VoIP call, so VoIP with video. Right, and the user on the other end picks up. Not much to see here. Right, and then we also start off the post detection application on the MRU. And it takes a while because I think we're using the H.265 codec. And then once it's set up, we can sort of see the post detection taking place. And similarly for the cloud gaming, we'll start the game. And the game's path of exile if anyone's interested. Right. So now we have our 3 applications running, and now we are ready to sort of start off the slicing use case. Right. So the first policy is we set the QoE for the mixed reality user as being a minimum of 40 and a maximum of 90. That's how accurate we want the post detection to be. And we push this through the RAP API. Right, and this is for slice 1 because that's the mixed reality user. And once we execute that, we can see that the policy is populated within the real-time, non-real-time. And then there's a corresponding throughput expectation for this environment that is set up. right? And then we can see here, this sort of triggers the CLA process where the XApp is now monitoring the performance and then adjusting the RB allocation. And any variation in the environment can trigger these messages, these rig control messages, right? So that's the debug log. And we'll be showing more of that as we go forward. We'll do a similar step for slice 2, where we set the min FPS to 50 and the max to 60. Right, and then we see a second policy is showing up here, which is for slice 2, which is our cloud gaming slice. Right, and now this also triggers the CLA for slice 2, and then we can also see an A1 policy being sent. Right, so this is what the network is in a sense in a baseline state where you've set your policies and the detection algorithms are working fine and so on. And then we extract these different QoS and QoE stats and put them on a Kibana dashboard to sort of visualize what's happening. And we can see that when the network is in sort of in a static state, you're meeting your throughput requirements, your MCS is stable, and your RB allocation is stable. So there's not much control being sent here. At the same time, we can see from the two graphs on the top, your QoE for MR is somewhere between 40 to 50, and then for cloud gaming, it's around 60. Right? And after that, we start off the mobility process for users 1 and 3. Right? So this is essentially a handover tester that varies the channel for the specific users, and then we are varying at a time step of 4 seconds. Right? So we're able to see some changes as a result of the CLA process. So it takes a while, but then we can see that our metrics start dipping, and this is what then continuously triggers your control request. So we keep sending control requests that try to match the throughput requirements with the RB allocation for our mixed reality slice. So we can see some sort of variation here if you look at the graph on the bottom left in terms of the MCS throughput and so on. But the idea is that we try maintaining the throughput requirements being set. So this means that as you lower your MCS, you need to allocate a higher amount of RBs, and this is being taken care of by the slicing assurance XApp. Right, so we see a throughput is around the same 30 to 40 megabit per second, but the RB allocation on MCS is kind of all over the place because of the mobility that's been happening. And the other slice is not affected because there's no mobility for that slice. Right, and now we stop the mobility and bring things back to normal. So we expect that essentially the CLA process should stop and our metrics should stabilize once more. Right? So that once that happens, we are ready to move on to the next policy, right, which is the second QoE policy. You can't. Okay, that's it, I guess. Well, there was a second policy, but it was something similar. So I guess nothing of value is lost. Yeah, any questions, I'll be happy to answer.